Welcome to the discussions on design and analysis of algorithms. So, we will start a new topic or a new paradigm from today's session, and this paradigm is called greedy algorithms. So, this paradigm is very closely related to another paradigm called dynamic programming, which I believe you must have covered. So, now we will start with one problem. Okay, first let's understand how we solve this problem. Then we will look into different aspects of greedy algorithm, followed by another very well known problem called Huffman code. Okay, so for the first problem we are going to do is called an activity selection problem. So the problem goes as follows. Let's say we have the schedule of several competing activities that require exclusive use of a common resource. Okay, so you are supposed to schedule, or you are having a schedule of several competing activities. Lots of activities are going to happen. Okay, but all of them will require an exclusive use of some common resource. So all these activities will use a common resource, so they will need that. Okay, so suppose we have a set S of A1, A2, An of n proposed activities that wish to use a common resource such as a lecture hall. Okay, so this is a very practical problem. You got one lecture hall and there are n events. Okay, you want to schedule which all events will happen. Fine. So you got these activities A1, A2 and so on. Only thing is that you can host one activity in this lecture hall at a time. That is, only one activity can be scheduled at a time. So each AIth activity has a start time and a finish time. So you know that it has been given that for every activity it will start at a certain time, it will finish at a certain time. Okay, so activity AI, if I take, I will denote SAI as start time of the activity and finish time as FAI. And we will say that the activity AI and AJ are compatible. Okay, so we will use this term called compatible if following holds: SAI is greater than FAJ or SAJ is greater than FAI. What does it mean? It is saying the start time of ith activity is greater than the finish time of jth activity. That means AI and AJ are compatible, means I started AJ at some point, I stopped right there, it finished at this point. AI has to start after AJ. Okay, so AI will start at this point after AJ finishes. So this is F of AJ, and that's start of AI. Okay, or it may be other way round, that AI finishes first followed by J starting later. So SAJ is greater than FAI. Fine. Okay, that means there is no common overlap. It cannot happen that jth activity will start somewhere before ith activity has finished, or vice versa. Okay, that will not happen. Then we will say that these two are not compatible. Okay, fine. So compatible activities are those where there are no overlappings of timings. Fine. Okay, now what is the problem? Problem is to, of course, select a maximum size subset of mutually compatible activities. Okay, so you have to select what? Maximum size subset. Okay, of mutually compatible activities. What is the maximum number of activities you can pick up to fit in your lecture hall? Okay, you want to schedule as many activities possible in this lecture hall. Fine. Let's say that you earn money from each of these activities. Then in order to earn more money, you want to essentially, put as many activities possible in this lecture hall, right? So you want to maximize the size of the subset of mutually compatible activities. Fine. Okay, I hope the statement is clear. Now, notice first thing. Here, it's a maximum, it's a optimization problem where we are asking to maximize something. In this particular case, we are asking to maximize the size of the subset of mutually compatible activities. Fine. Okay. So it's a optimization problem. Typically, we use greedy algorithms to solve optimization problems. Okay. So now we will do the following. Hearing the problem, it looks like, okay, we will start approaching the problem in the following manner. We will say, okay, let's select among the available requests that starts earliest. Okay, let's start from the very beginning as soon as possible. Let's pick up the activity which is starting the earliest. Okay, then whenever it finishes, I will start the next activity, next available activity. Okay, so we will select the available request that starts earliest. Okay, so we'll go by the earliest starting time of activities. The question is whether this will give me an optimal solution or not. Fine. So here is an example which shows that we will not get an optimal solution. How? Let's say I got this 5 activities. So this is the timeline. Okay, let's say this is the time. Okay, and this is the activity number 1, or let's say this is A1, A2, A3, A4, A5. Okay, now notice that the start time of A1 is the earliest. Okay, so this is the time starting from 0. You may take this as 0. Okay, fine. And what we say that, okay, out of this A1, A2, A3, A4, A5, I have just numbered them randomly. Okay, I ask the question, which one is starting earliest? And it so happens that A1 is starting earliest. So if I choose A1, how many activities I have selected out of this set of 5 activities? We have selected only 1, right? So my solution is having a set A1 whose cardinality, so if I denote it by S, cardinality of S is 1. Question is this optimal? And the answer is no. Looking at the picture, you can see that if I select A2, A3, A4, A5, so if my solution is, let's say, S1, and I select A2, activity A2, A3, A4, A5, then each of these activities are compatible with each other, right? They do not have any overlap. They do have an overlap with A1, but amongst them, A2 is not having any overlap with A3, A4, A5. A3 is not having any overlap with A4, A5, and so on. What is the size of S1? 4. Which one is maximum? Definitely this one is maximum, right? So the optimal solution is this one, right? So if we start by the earliest start time, then I might not have the optimal solution. But it looked like a very reasonable choice. Fine. So now what we did, we showed that, okay, this strategy of this choice 1, is going to fail. So we make another choice. So we say that, okay, let's choose the smallest intervals. Okay, that also makes, you want to choose the smallest activities. Okay, so that you think that, okay, then I will be able to accommodate many activities. Okay, that looks like a reasonable choice. Fine. Now again I will show that also doesn't work. So here I have 3 activities. Let's say this is A1, A2, A3. Okay. Now our choice was what? Choose the smallest interval. Now notice that this guy is the smallest interval. Okay, these two, A2 and A3, are large. Fine. Interestingly, notice that A1 is not compatible with A2, A1 is not compatible with A3 because there is an overlap. There is an overlap, right? But A2 and A3 are compatible with each other. Fine. So, by this strategy, I am going to choose the smallest interval first. I will choose which one? A1 in my set S, right? If I choose A1, can I choose A2? I cannot, because A2 is having an overlap with A1, so they are not going to be compatible activities. Can I choose A3? No, I cannot choose A3 because A3 is having a overlap with A1. It's not a compatible activity, so my solution is A1. Cardinality of S is 1. Now I say that, okay, if I choose the solution as follows, A2 comma A3, what about these two activities? Are they compatible? Yes, they are compatible activities. What is the cardinality of S1? It is 2, which is larger than cardinality of S. So which one is optimal? S1 is optimal. Fine. Okay. So this strategy of choosing the smallest interval is also not going to work. Fine. Now, interestingly, we will choose again using a different strategy. So we choose saying that select the interval which ends first, but still not overlapping the already chosen intervals. Okay. So what you do, you essentially take all your activities, sort them by their finish time, pick up the interval which ends first. Okay. Then you will look into the remaining set of activities you are having, and then you will say that, okay, let's select the activity which ends next, and so on. And you can see that this is going to work for all our previous cases. Okay, so let's see how it is going to work in all our previous cases. Now notice that if I go by the finish time, which one is finishing first? A2. Which one is, so I will pick up A2. What are the remaining activities? Remaining activities are A1, A3, A4, A5. Fine. Then which one out of these activities, which one is finishing first? A3 is finishing first, right? Because these are the finish times of A3, A4, A5 and A1. A1 is the one which finishes last. Okay. So I'm going to pick next activity as A3. Remaining activities are A4, A5 and A1. Out of this, which one finishes first? A4 finishes first. Okay, fine. So then I will choose this one, right? Then what are the remaining activities? A5 and A1. Out of these, which one finishes first? A5 finishes first. Okay. Then I have A2, A3, A4, A5. What is the remaining activity? A1. I cannot put A1 in it because A1 is not compatible with any of these. Fine. So this strategy which we just stated is going to work for A2, A3, A4, A5. It's going to give A2, A3, A4, A5, and that's my optimal solution. We just saw that. Okay. Let's look at this example. In this example, what happens? Out of A1, A2, A3, which one finishes first? Of course, A2 finishes first, right? Then you pick up A2, the activity A2. Then what are remaining? A1 and A3. Which one finishes first? A1 finishes first, but of course A1 is not compatible with A2, so you have already selected A2. You cannot select A1 because A1 is not compatible with A2. So which one do you select? The remaining activity amongst the remaining activity 1 which is compatible with A2, that is A3. Okay, so you select A3. Fine. Is this your optimal set? Yes, we saw that this is our optimal set. Fine. So we can verify for both of these cases that yes, this strategy, this choice we made is going to work. So we said that, okay, select the interval which ends first, and of course you need to see that whatever we have already chosen, it should not be incompatible with already selected intervals. If it is compatible, then you choose the you choose the interval or activity which ends first. Okay. Now you need to verify that it works in all cases. Fine. Okay. We verified that at least for these two cases which we just discussed. Of course, we cannot verify for all possible cases. We need to prove it that it always works. Okay. So here in this example we just showed, in this example also we just showed. Okay. So now the question comes, okay, that why is this strategy going to work? So the algorithm gives, first of all, notice that it gives always non-overlapping intervals. Okay. So that is obvious, since we are always choosing an interval which does not overlap with previously chosen intervals. Okay. So what you do, you first take all the activities. So even though I am showing intervals, here I mean activities. Okay. So you first take all the activities, sort them by their finish time. Okay. And then you choose the one which finishes earliest. Once you have chosen that one, you look at the remaining activities. Within the remaining activities, those ones which are not compatible with whatever you have already chosen, look into the remaining set of activities which are compatible with the already selected set of activities. Within them, you choose the one which finishes first, and you keep on doing this. Obviously, the activities which you are choosing are not going to overlap. Fine. So the interval is the time interval of each of these activities. Okay. And this solution is exact. So let's say A be the set of intervals obtained by the algorithm, or the activities obtained by the algorithm, and O be the optimal largest set of pairwise non-overlapping intervals. We want to show that A must be as large as this optimal. Okay, fine. So that's a typo. This should have been optimal. Okay, fine. So what it is saying is we need to show the following. We need to show that using this strategy, whatever is the set of intervals or activities we will select is going to be as large as the optimal solution for the problem. Okay. So my strategy is going to work. So let's try to prove it. So let's say AI1, AI2, blah blah blah, AIK be the set of activities in A in the order they were added to A. Okay. So note that A is equal to cardinality of A is K. Fine. So what we are saying is, what is A? A is the solution obtained using our strategy. Fine. Our strategy said that first you sort them by finish order, and then you start picking them based on this finished order. Okay. So you pick up the one which has finished earliest, and then you look for the remaining set of activities which are compatible with your chosen activity. Okay. Within that, again you pick the one which is finishing earliest. So let's say your solution using this strategy comes out as you have picked up AI1, AI2, blah blah blah, AIK. So how many activities you have picked up? K activities. Okay. Let's say in your optimal solution you have AJ1, AJ2 till AJM activities selected. So first thing you want to prove is that definitely you want to prove that K is going to be equal to M. Okay. We want to prove that K is going to be equal to M. Okay. So let's see how to prove that. So essentially, in order to prove that, first thing we will show is that for all indices R less than equal to K, we have the finish time of FAIR is less than equal to FAJR. Okay, what it is saying? For all indices are less than equal to K. What is K? K is the total number of activities selected by our strategy. If we do that, what it is saying is, first we prove that the finish time of AIR, the activity AIR, is less than finish time of activity AJR. So what is AJR? AJR is this activity in the optimal solution. Okay. So what we are saying is AI1, finish time of AI1 must be less than finish time of AJ1. Finish time of AI2 must be less than finish time of AJ2, and so on, for all r less than equal to K. That's what we want to prove. And we are going to prove this using induction. So first is the base case when r is 1. So the greedy algorithm is going to choose the activity with earliest finish time, right? We said that we are going to choose the activity with earliest finish time. So definitely activity AI1 must be finishing before any other activity. So it is less than equal to finish time of AJ1. Fine. So this definitely holds true. Then we have the induction hypothesis, where we say that, let's say that the statement is true for r minus 1. Okay, for r greater than 1, because we have already shown it is true for r equal to 1. So let's say the statement is true for r minus 1 for r greater than 1. That's our induction hypothesis. And then in the induction step, we show that, okay, so essentially using this induction hypothesis, we must be having f of AIR minus 1 is less than equal to f of AJR minus 1. That means AIR minus 1th activity is going to finish earlier than FJR minus 1th activity. Fine. Now notice that your SAJR, the start time of JRth activity, is definitely going to be more than the finish time of JR minus 1th activity in your optimal set. In your optimal set, you are having this AJR minus 1, and then you will pick up AJR, right? So the start time of AJR must be greater than the start time, finish time of AJR minus 1 in order to be compatible with each other. So that holds true, but we have already taken it from our induction hypothesis that FAJR minus 1 must be greater than FAIR minus 1. Fine. So it comes from this fact. Okay. Which means what? That the interval AJR, which is in my optimal set, is going to be compatible. So thus the interval AJR is in the set S of available activities at the time when the greedy algorithm selects AIR. So my greedy algorithm selected AIR, right? After AIR minus 1, it selected AIR. Fine. And the optimal solution, some other algorithm which figured out the optimal solution, it selected AJR. Okay. But what we showed is that the start time of AJR must be greater than the finish time of AIR minus 1. So the greedy algorithm selects the available interval with smallest finish time. Since interval AJR is one of these available intervals, we have FAIR is less than equal to FAJR. Now look at the following. Can I have this situation? Can I have, of course, AIR minus 1 by the induction hypothesis? FAIR minus 1 is going to finish earlier than JR minus 1. And my JR is compatible with JR minus 1, so it is going to start later. So SAJR is greater than the finish time of AJR minus 1. Okay. And of course, then it is greater than FAIR minus 1. Question is, can this activity JR finish earlier than the activity IR? And the answer is no, right? Because if this one finishes early, which one do I choose? Why will I choose IR? I should choose JR, right? Because we always choose by the activity which is finishing earliest among the possible compatible activities. So JR is, we already showed that JR is compatible with IR minus 1, right? The start time of AJR is more than the finish time of AIR minus 1. So JR must be compatible with IR minus 1, and it is for finishing earlier than IR. So I must pick JR, right? Okay. So essentially what it is saying is, then if I am picking IR, it must be that the finish time of FAIR is less than equal to finish time of AJR, right? And that's what we wanted to prove, that finish time of AIR is less than equal to finish time of AJR. Fine. So hence we have completed all the steps of the induction, and we have proved the fact that FAIR is less than equal to FAJR. So this case cannot happen, right? If my algorithm is picking up AIR, then IR must finish before FJR finishes, right? Okay. So finally, we have the last theorem which says that the greedy algorithm returns an optimal set A. It is going to return the optimal set A. How? So let's say A is not optimal. What is A? A is the solution obtained by our algorithm. Our algorithm is what? We will, sort all the activities based on their finish time, and then we will pick up the first activity, whichever finishes earliest. I will put it in A. Then whatever are the remaining activities, I will look into them. Look at only those activities which are compatible with whatever already has been picked up in A. Within those activities, you pick up the one which finishes earliest. That's the strategy. So let's say A is not optimal. Then optimal set will have more intervals, right? Because it's a maximization problem. So M must be greater than K. So the first claim is, let's say M is not equal to K. Right? K is the size of the set of A. Our solution says we will get K activities. Okay. Somebody says no, I will get, my optimal will be M. Okay. Where M is greater than K. So now what we have proved from last lemma, that finish time of AIK must be less than equal to finish time of AJK. So the AIK activity selected by our algorithm is going to finish earlier than whatever is the optimal strategy, that AJK activity. Fine. Now since M is greater than K, that means in the optimal set we have more than K. There is an activity AJK plus 1 in O. O is the optimal set, right? So then this request is after AJK ends, right? Because in my optimal set we have selected AJ1, AJ2 till AJK. We have already proven that finish time of AI1 is less than finish time of AJ1. Finish time of AI2 is less than finish time of AJ2. Similarly, finish time of AIK is less than finish time of AJK. But since my optimal set is having more number of activities than our choice A or our solution A, then I must be having this activity AJK plus 1 in my optimal set, and this must be coming after AJK ends, right? Okay. Hence AIK, and hence definitely it will be coming after AIK ends. So I have AIK. It is finishing somewhere here. AJK is going to finish later, right? Finish time of AIK is less than finish time of AJK. We have proved that. And then I am saying that, okay, in my optimal I got another activity AJK plus 1, right? Okay. Then this activity must be starting later than AJK, which means that this activity must be starting later than FAIK. That means these two activities are compatible. So if these two activities are compatible, then according to the way we are choosing in our algorithm, I should have picked this activity. I will not stop, right? So there lies the contradiction, that I must have stopped there at aik is not right. I must have picked up ajk plus 1 also in my algorithm A, right? Okay, so that's why I have a contradiction. So that's what it is saying. So after deleting all requests that are overlapping with request AI1, AI2, AIK, the set of possible activities S still contains AJK plus 1, but then the greedy algorithm stopped because S was empty. So you have a contradiction. Fine. Okay. So essentially, what we proved is that this strategy is going to return an optimal set A. Okay. So that's our first greedy algorithm. We will look into quickly two different ways to implement this algorithm, and then we will see what are the basic rules or properties of any greedy algorithm. So we'll stop at that. Thank you.